will work.
Do you play
I'm going to talk about
I do.
I'm gonna write it for Facebook on every time.
I mean, you have the notes for it. It's classic, essentially.
Yeah.
if you want to collaborate.
Now, do we need calculators for this?
Yeah.
Oh yeah. A lot of ideas on that.
So lovely.
I didn't say you're gonna stand.
Radius.
Talk about the.
Is that a 7 microcoulombs?
Yes.
I was
This is gonna be the most easiest problems they do.
It's for
The
Morgan.
radius would decrease to get to 0.32 meters.
It should work. I hope.
No one likes.
Other than that, my only complaint is that I have no idea how to do this.
Got time.
Yeah, it's just the same thing.
Oh, no.
You never took stat.
That's
then.
correct. They're,
Oh,
they're
it's in
referring,
stat.
they're referring to the
Well, no,
Gaussian
I just use one
surface.
stat. Because you'd have to like write the same thing out like 3 times.
Gaussian surface.
So
for, like,
our
stupid
Gaussian
conditions,
surface
so
is
you just-
not going to be a
The
radius
hypothesis,
0.75.
every hypothesis, you write out the null,
Yeah.
with quotation marks, did not happen.
Right? Don't look at me. I told you this is gonna be the staring contest. The Gaussian surface.
You'd be surprised
Wait.
how long I could stare at something.
Yeah, how does it,
The Gaussian surface.
oh, the rate,
Radius of the Gaussian.
But we're looking for the flux through the cylinder, so the Gaussian surface, at least in my mind, should be on the cylinder.
Doesn't have to be. You can put a Gaussian surface in.
Right, but we're looking at it through the cylinder, so
First, you're looking at it along the line of charge, and you're looking at it in the radius of the Gaussian surface. And you're looking at it flux through the length.
alright, so we've learned one thing. The radius of our Gaussian surface must be below 0.32 meters. We've learned something, gentlemen.
yeah, it's true. 1.32.
Now, how many integrals do I need to solve this problem?
None. There are no integrals.
Then I don't know how to do this problem.
That's right. That's right.
Should there be an interval over a closed surface?
Just or flux. Flux A.
Flux.
Flux equals Q.
Q enclosed over E. Is it just Q enclosed over E? Or E naught?
Now, is it talking about the length of the cylinder? Just checking.
Is it
Joe, Joe here is making some very good observations. It's just a take off.
what did Joe say? Joe, what
Hey,
did you say?
Joe, what are you saying? You're answering A, so give the logic that you're going
I'm
on.
just saying that we need to find Q, it's just 7.5 microcoulombs.
You're saying you need to find Q, what else are you saying?
Yeah, and we just, we put that over the,
So what equation do you basically use?
Q,
Okay, so you're saying flux equals Q enclosed over epsilon sub zero. Okay, that's what he's proposing. He's having a problem with the top part. He's saying it's 7 microcoulombs. I'll give you a hint, Joe. Don't let anybody say anything. It's 7 microcoulombs per meter. Mr. Dillon, say it. You went a little too far. Stop. Okay, all right.
I knew that.
You're saying do this. That's Mr. Del Rossini's suggestion. What is that gonna do, though? The meters are gonna go out, so you're gonna get the charge, okay? And then Joe is suggesting just divided by epsilon sub zero, which is 8.85 times 10 to the negative 12. Okay?
I thought that was 10.
Meters squared per
That's
coulomb.
K.
And you'll get the answer. And Joe's absolutely correct.
What?
K is not epsilon. They're two different things.
So the
K
what is he
is
talking
one,
about
no,
when the
K
radius
is 1
increases?
over 4 pi times E, the zero.
What does our Gaussian surface look like in this case?
You have a Gaussian surface emanating from the radius center line at 0.32 meters.
At what?
At 0.32 meters. Okay. Anybody get the first part?
Yeah, I have a number.
You have a number.
Yeah, 4.7 times 10 to the fifth. I think.
Whoa.
Yeah, 4.9. Wait,
No.
Mu coulombs, that's 7 times 10 to the negative 6.
Mm-hmm.
Sorry, I
What?
just...
3 people got that, and I did.
No,
All right, B. B.
Okay, no, finish A. What does our Gaussian surface look like for A?
You're on the line.
What?
You're to the line of charge. Your Gaussian surface is right on the line.
I don't understand.
Draw a picture.
Picture.
Draw a picture.
Hey, here we go.
So yes, we have a cylinder we're looking at,
You have
and
a
we want
line-
to find the
line
flux
of
through the
charge.
cylinder.
You have a line of charge.
And we want to find the flux through the cylinder.
Our Gaussian surface is right on the line.
But we want to find the flux through the cylinder itself. And we can only detect the flux as it goes through the Gaussian surface.
Right. And the
So
Gaussian
wouldn't we
surface-
want to move our Gaussian surface out to where it matters?
Maybe you want to. They want the
Everything
flux-
you've told me so far
But they
has
want
led me
the
to
flux-
believe.
They want the flux through the cylinder just due to the line of charge. No, we're on the line of charge.
Then they don't want the flux through the cylinder. They want the flux through a different cylinder we're constructing directly on top of the line of charge with radius of 0.
Radius.
So there
is-
wouldn't be a cylinder.
Yes.
So they gave us one cylinder and then want us to completely ignore it.
They,
We're not actually using that cylinder for anything except to tell us that we have a
need the
length.
length. You need the length.
Then why not just tell us we're looking at a 0.6 meter stretch of an infinite line of positive charge?
Yeah, you could phrase it.
Then why give us the radius? It's extraneous information.
That's correct. Actually, it's not extraneous information because of part B.
That's the radius.
It
of
seems
gas
to be
surface.
because we're giving a radius that is still not the radius of the cylinder we're given.
And that's a very good point. So what's the answer to part B?
Same thing.
Same
Huh?
thing.
What?
I don't think it
He
can be
said
the same
zero.
thing.
Chris, what did you say?
Zero.
No, something else.
Same thing.
Why are you saying the same thing?
Because radius
Because
is
we didn't
in
use
another
radius
part.
in the first part.
Well, yes.
The length of the cylinder did not
The
change.
length does not change.
The length didn't change. What is the?
We don't
Come on,
charge.
Scott, go. Come on, Darcy.
Just trying to see.
Zero.
Is the.
Don't go with the length.
Well, it's the charge per length, so if you change the radius, it doesn't change the charge.
Oh,
Well,
nice.
what about the radius?
The size of it.
We didn't even
doesn't
use the
matter.
radius.
Yeah.
The length, unit charge is something.
Yeah, it's extraneous.
Nah, it's not extraneous.
It's tiny.
Something else too.
Constant.
Oh, does the charge per unit length decrease proportionally?
Constants
Don't
bother.
Don't bother us, guys.
What about the radius?
0.6.
That makes sense.
0.75.
The object has a radius of, the object has a radius, don't look at it as a cylinder,
The larger the radius, the cylinder.
but don't look at it as a cylinder, look at it as a sphere. The radius of the
$0.9.
sphere is 0.8, and they're asking for the flux at a radius of 0.32. Charge located dead center.
It doesn't
We only detect flux going through the Gaussian surface.
What happens if you exceed 0.75?
Electric charge resides on the surface. That's rule number one. That's rule number one.
Right.
That's actually summary number one, not really.
Well, Chris's comment that is the same is correct.
Wait, thanks guys.
Then why'd you go through all the BS over there?
Somebody BS.
The answer is. We just finished saying it wasn't radius. Are you mad?
Yeah.
So make up your mind. Does the radius matter? Does it not matter?
It does matter, as long as you're within 0.8, you're good.
Why 0.8?
Where's point A come from?
Yeah.
Number
Actually,
three.
within
See?
0.75. Within 0.75.
Oh, because that's the cylinder.
So what if it was bigger?
Well, then you're outside the cylinder.
Okay, so the electric flux is the same everywhere from the wire itself out to the cylinder. Yeah?
And the radius doesn't matter with it.
But the electric field does not exist between the wire and the
So
cylinder.
if the Gaussian field had a radius greater than the cylinder, what would that be?
We haven't gotten to that. We haven't gotten that to that specific yet.
But that's what you're saying. So you're saying when the Gaussian field is in the cylinder, the radius doesn't matter.
As long as you're closing the charge.
So we
As long as the charge goes through the outside.
we didn't increase the radius of the cylinder. We increased the radius of the Gaussian surface.
Genius.
I'm so confused at what.
Don't worry, Carter.
For one, how do you increase a radius from 0.75 to 0.32? Short.
No. It's look, when you have the cylinder, and you have a Gaussian field in the cylinder. The
That's literally what I just said.
And you just said how you.
The Gaussian surface increases the
Hopefully, we're
flux.
gonna get to an example
Yes.
That's literally what I
later.
said first, and you guys said no.
Carter, hopefully we're gonna get to an example a little bit later with a cylinder with a hollow cavity. And we're gonna move the Gaussian surface. You'll see what that does.
Alright.
Okay, these problems sort of lead into each other, and I'm intentionally making it a little cryptic to cause you to be able to start to question and think a little bit. I know this is very aggravating.
No, I'm not aggravated at all. I'm not
Well, I'm
angry
glad
in
you're
any
not getting
way.
it. I'm glad you're not getting it, because you're asking.
It's going to show on the test.
No, because I want you to not initially get it, so as we go further into the examples, it's gonna become clearer and clearer.
You're doing a fantastic job with the first
What is
part.
proper definition?
What is that passing?
What's
Is it actually there, or is it just like
As I understand it, the Gaussian surface is something that just arbitrarily
Number
draw
of
electric
real
field.
line plus
Like it's not
out,
actually
plus
there.
an outlet
Eventually,
to a
we'll-
closed
Eventually,
surface.
as long as we're turning.
It's just, going out.
go out.
Just finding the number of lines.
Yes, essentially you're finding the number
So
of
if you
lines,
draw us a picture.
which is limited by the limited in its density by the permittivity of free space concept.
So if you draw us a picture of like a circle, you say this Gaussian surface, and you draw 8 lines outward, and you ask us what the flux is. If I put 8,
There are 8 flux.
Depends where the Gaussian surface is.
Oh, my.
no, you didn't draw anything but a Gaussian surface.
And
You just drew me a circle and said this Gaussian surface with 8 lines coming out, flux equals 8. Correct or
What do you
no?
want me to do? You draw the Gaussian
Draw me a
surface.
Gaussian surface.
A
A potato.
Gaussian surface.
A potato.
Now
There
draw
are now
8
8 lines.
through it.
Make it easier, 3 lines. Just draw 3 lines.
Is the flux
There are
through?
Flux is 3.
3 flux.
Yes.
Yeah!
That's the first thing I've understood so far.
One example.
Use that short.
You know,
Multiple choice question. What is the flux of this Gaussian surface?
Well, believe it or not, there will be questions that simple.
Just count the lines.
Well, not so much also count the lines.
Count which ones matter.
Also look at where the surface is and where the charges are that are closed by the surface.
So the lines going out of the Gauss surface, not Gauss, what is it? Gaussian surface, not a real surface.
Not a, well, Gaussian surface is on the real surface.
So are we just
But
like
if it's-
saying,
if it's-
it looks like there's Gaussian surface right here.
Flux equals the amount of lines coming out of the Gaussian.
Here's
Write that
a
down.
plain, don't copy this. Here's a plain sheet,
Okay.
a plain metal sheet with charge sheet. What Gaussian surface can I draw?
Anything.
Yeah.
Nice, partner.
Actually, we're gonna see, not now, okay, because we're looking at capacitors, which are essentially parallel plates. I could draw a cylindrical Gaussian surface that includes through those plates.
So wait, Mr. Rega.
I can also draw,
So it doesn't have to be
oh, that looks like that.
So Mr.
Yeah.
So is a Gaussian surface a physical thing?
No, it's an imaginary construct.
Wow. So it's like we draw this construct to determine things about the actual object.
Yes, yes.
We just count the lines outward.
Yes. You draw a Gaussian surface, it's an imaginary construct to determine the properties of the electric flux, the electric field, through a actual object or in a region of space.
How did the
Flux equals the amount of lines.
what do you do to prove that?
The experiment?
Yeah.
You're actually gonna do
Really
an
hard.
experiment.
I know.
Okay, this is the basis of, this is the basis of a capacitor.
Okay.
I don't know how much electronics you know. A capacitor is a device which stores a charge.
Let it all out real quick.
Alright. I do know what I'm talking about.
I don't.
I have no doubt in my mind that you know what you're talking about, but none of us know what you're talking about, so there's a communication.
It's intentional.
Then please just continue and move on to L equals 0.8, and we'll stay confused.
Delta Y.
Here's, Faraday did an experiment, which you're gonna look at when you come back to the senior trip, called Faraday's ice pail experiment. She took an ice bucket, and like this.
Okay.
Okay, now, if you put a charge into this bucket, what she did by taking a charged ball, head ball, and put it with a string in here, the question is, what happens to the charge? So if I put a positive 3 charge here, Joe, where is the positive 3 charge? It's detected on the outside surface, provided the outside surface is neutral.
Isn't that the experiment we just did?
Yes.
Wow.
So where's the Gaussian surface?
Good,
The
good.
experiment we
Good.
just
Wherever you
did.
want to
is
put it, Alex.
Kelly, good poll, Kelly. So what maybe you should be talking about in this lab report?
Faraday's.
Okay. So, no, I don't.
That's all you.
She even checks in the last night.
Yeah, and the one lab group will be able to say something even more about it. So anyhow, now here's the thing: to make a capacitor, that'll store charge. Faraday was able to store charge with this. This will store charge. But if I put a material there, and put another pail and charge it, now I have a cavity within another object. To keep it separated, I can have air, but I could put a material. Okay, and this is going after you come back from the senior class trip. The nature of this material will determine how much charge this can store. Okay, it's called dielectric, how much it can store. Okay, so the fact of the matter is, here's the really good question, which we won't answer now. Where the hell is the Gaussian surface?
Wherever you want it.
Good answer. That's absolutely correct.
Now, if only we could see the lines coming out of it, because we could just count them. And then
Gaussian surface behind the end.
Okay, so it gets a little freaky.
Let me see us a little bit. Yeah, you're drawing all of it doesn't have to be in the actual object like with the cylinder, right?
Correct.
Some of it like
Are we gonna have to decide what the Gaussian surface looks like when we problem? Well,
What is the relationship with the Gaussian surface with the object? I don't get that.
Whatever you want.
well, let me answer this question first.
That is useless. That is absolutely useless. There's no
I'm going to
relation.
give you a procedure for looking at the problems. One of the procedures, and it's sort of something I've clobbered together from doing various problems. One of the procedures will be is you're going to have to make a judgment on the object.
Making the most
But
of the
I'm going to give you some
situation.
guidance
Smart.
that there's to simplify Gaussian calculations. They use what's called the property of symmetry. There's spherical symmetry, cylindrical symmetry, and then there's basically flat plate symmetry. And if we ever get to it today, which I seriously doubt, I was going to show you, we'll get to it tomorrow, spherical symmetry. So there's certain symmetries that you can say, oh, that object, my gut feeling is spherical symmetry would work the best.
Okay.
So if you make that decision, then there's a certain basic pattern that falls after that. And the only time it gets weird is when you're dealing with objects or point charges in space and you're going like, you know, then but we're not going to get to the point that you're going to be doing that. Jared, what was your question?
What is the relationship of like a Gaussian surface to an object? Because it seems like there is none, and then why are we doing it? I'm really confused by that.
What is the relationship in terms of
Like for the problem, we found the Gaussian surface is like a smaller cylinder inside a big cylinder, but then we're saying you could pick whatever you want, and it's throwing me off.
You have to, it's like your observation zone. It's like where you want to observe.
But in the problem, it seems like we didn't choose it in the problem.
This is going a little bit ahead of us here. Let's say you had a solid sphere with a cavity in the middle. I could put the Gaussian surface there.
Yeah.
Okay. Put it there. Put it there.
Oh.
Depends on where you want to know the charge.
Depends where I want to know
How the charge is.
where the flux is.
Flux.
Okay,
Flux.
the electric field. If I put it here internally within the cavity, it would be equals 0. Once the field penetrates the Gaussian surface and comes here, I'm going to detect something else. We're going to get into that a little bit later, what that actually means.
So in the problem, we're making an infinitely small cylinder along the line of charge. Is that why
For
we
part
chose
A,
that?
basically, when we're saying the Gaussian surface, I'm giving you the wording that the way the problem is stated, which is poor wording. What we're saying is the Gaussian surface for part A is on the center line. You're
And
literally
we're
on
gonna
it.
find the flux on that line.
Right. Now, when we increase the radius of the Gaussian surface from it, because the charge is still enclosed, the flux didn't change. Okay. Now we're getting to part C, finally, of the first problem. Moving right along, okay? All right. What would happen?
You just multiply it by 0.8.
Yes, exactly. Nice. Very good. The only thing that changes is...
Oh, wait, now it's outside.
We need to get like the Family Feud sound effects. Like when you get
Ah,
the answers, like
the length change.
the big X line.
So the longer the cylinder is, the more flux it can
Well, the Gaussian surface is right on the line.
Oh, okay, so you're stretching, okay, so, okay.
The Q enclosed by the Gaussian surface is increasing.
Right.
The radius on the cylinder you gave us is an upper bound on how large our Gaussian surface can get that away. So why isn't the length of the cylinder an upper bound on the length of our Gaussian surface?
Well, the length of the cylinder, you could adjust physically the length of the cylinder. If you're putting the Gaussian surface right on that line, you can stretch the length of the Gaussian surface. Or would you have to stretch the length of the Gaussian surface?
Wait, did it say?
Is there gonna come out of the cylinder?
You're finding the flux through the cylinder, so.
Yeah, I would think if we go to 0.8 meters, then some of that charge, in fact 0.2 meters of that charge, is no longer enclosed by the cylinder we were given.
No, you're making the cylinder.
You're
making the cylinder bigger.
You're stretching the cylinder.
Ah,
Yeah.
okay.
Yeah, you're not, it would, that.
So in part
That's not the
C,
Gaussian
in part C, we're physically changing the cylinder.
Yes,
In part B,
yes.
we are not.
Part
No,
B is the
right,
Gaussian
part B,
surface, but
that radial change is the change in the radius of the Gaussian surface.
All right, that was
There's no
unclear.
difference between how they're written though.
Yeah, are they gonna tell us?
Are they gonna
what-
be written different?
This is, I took this problem directly from, not your physics textbook, another physics textbook. And this is exactly how I know.
That's terrible.
It's horribly worded. I'll word it better.
I think you should have changed the
We should do one with good wording first, and then work our way into the one with bad wording. I support that decision.
I gotta tell you, when I learned this in college, I got through the same thing you did. I was very frustrated. I didn't really understand it. I got to the test and I went, bleh.
I fully
Okay.
understand this.
6.3 times 10 to the.
You draw a random shape on a charged object,
Not a random shape.
a very random shape, and then you count the lines outward.
Well, a shape with a purpose.
Listen,
what you're
if you
trying
got
to
the
find.
AP
Yeah.
test,
You can't draw.
Carter, I'm gonna ask you, if you got the AP test and they said to you, I have a charge Q floating in space, and I wanna know the nature of the electric field intensity around that charge, which Gaussian surface would you draw?
Circle.
Sphere. It sort of makes logical sense.
A circle.
I would say it doesn't matter because it's just Q over E naught, no matter how you draw it.
If I wanted to write a more specific equation, which we are going to do.
But I mean, you could draw a square, right?
You could, but a sphere makes more sense.
I guess if.
Equidistance on every.
Yeah, right.
Word. I know words were.
But what about?
That would make it equipotential,
You want to
right?
see another example? Or
All
is it
points.
two in the notes?
I keep going all day.
I'll leave it to your discretion.
I think I better do another example.
Yeah.
Okay, this is going to take a little longer than I thought. Maybe I can find an easier example.
I mean, that was hard, I feel like I learned.
It's pretty challenging.
Well, I think they.
All right, you should look at this one. Small spheres are enclosed in a surface.
Okay, maybe compare it to battery and we should probably start with the big one first, and then once we have base.
Get their paintings involved. Actually, for the first time, I'm not falling behind you. Because everyone else is so far behind as well. I feel like I'm in the back. I feel good.
They've already been running for a while or something.
Find the flux through what I'm following?
Each of the following closed surfaces.
S?
So I have three small spheres enclosed in a surface. Q1 is 4 nanocoulombs, Q2 is negative 10 nanocoulombs, and Q3 is 5 nanocoulombs. Surface 1 is enclosing charge 1. Then I put Q2 being closed by a surface. Then I put Q1 and Q2 together and closed by a surface. Then I put Q1, Q2, and Q3 together and closed by a surface. I want the flux through each of those surfaces.
E equals KQ over R.
Huh?
Squared. R
You don't
squared.
have an R.
I just can make one.
Yeah.
Do we have to sum charges?
I'll leave that up to you. Come on. Yeah, surface 1, surface 2, surface 3, surface 4. Kelly, you're mumbling. Do you have a guess?
How can we find flux if we don't know the radius? And even if we can make one, it's just going to be random. Like his answer would be different from
No, you
mine.
have an equation that you could do.
We don't need the radius for the.
We just need Q
What is
enclosed
three
over.
spheres enclosed on the surface?
I have 3 charged balls.
So they're next to each
Oh,
other.
Q1, Q2,
question.
Q3 are the spheres?
Yes.
Oh.
Yes. Yeah.
Who let
Do
him in
signs
here?
matter?
I don't know.
Oh my god. That's a lie, you do know.
Yeah, I feel like you're lying to me on purpose.
You can't trick me.
You should be able to answer that question.
They always matter, except for when you tell us they don't matter.
Can anybody, Q1 you should be able to get. S1 you should be able to
There's
get.
no absolute value. So I'm gonna
What's
say
S1?
That's
Anybody have a numerical answer for S1?
Q1 over the constant?
40.
Anybody?
4 nanos.
452?
Good. What'd you get? 452.
Man, look at me.
Flux equals Q enclosed over epsilon sub 0, which equals 4 times 10 to the negative 9 over 8.85 times 10 to the negative 12, which equals 452 Newton meters squared per coulomb. Okay? How about S2?
Same thing.
Is it Coulomb squared or just Coulomb?
Just coulomb. The 8.85 is Newton meters, is Newton meters per coulomb squared. Let's jump the coulomb on top.
Wait a minute. It's 0.
Does sign matter?
Surface 2 is 0 because the lines are going in.
It should be a vector.
I know, but line.
It's a vector?
1130?
It's 0.
negative?
No, it's 0 because the line. Remember, flux is only the lines going out. The
Positive or
lines are going
negative?
in.
Negative. This goes negative.
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 Flux is 0.
Okay. Not for the reasons you people are giving.
No, I do the same thing. Yeah.
Why is it negative?
Because the line coming in.
Right, because the line's
I thought the lines had to go out. Isn't flux only the lines going out?
Yeah, but I told you yesterday, if it's,
If it's negative,
if
then
lines
it's
come in,
going
it's negative. So if you have a negative charge with a sphere, don't the lines go into a negative charge?
So flux isn't just the lines going out.
I'm so happy you're wrong.
The line's crossing.
Crossing.
I thought I understood this for a split second. Alright, so the lines can come back in.
It's a negative charge. Remember, the lines come into the negative.
Yeah, but I thought we. I was very specific when I said the lines. Count the lines going out was the flux. I
Within
figured
the
that.
Gaussian
When it goes in,
surface.
it's negative. When it comes out, it's
In the
positive.
Gaussian surface.
So
the
we have a
electric
little
field
picture.
must
So
vary.
the flux equals 0 because the negative is equal to 5.
The electric field equals 0. Flux is measured as it penetrates the surface. Flux by definition is number 1. Crossing through the surface.
Just crossing through. Once you add both.
Let's see. Anybody get the third one?
Negative 678.5.
Negative 678?
We add it.
Negative
Do we use symmetry? Do we use symmetry?
What do you mean by symmetry?
I don't know.
Sphere. You can use the cylinder because you're gonna have 2 points like on the thing. It's 2 points on a line.
Well, I summed them, so I got negative 6 nanocoulombs, and then I multiplied that by 4 pi k.
So, what did you get, Jason?
Negative 678.5.
We'll say 6, 7.
Every time I think I have a brain blast, just completely shut down.
Okay.
That wouldn't even make any sense.
I see it. Didn't
That
he
would
right?
make sense.
Was he supposed to sum them?
I assume.
Would you agree they're both enclosed by the surface?
It wouldn't make sense to multiply them.
Yeah,
That's
That would be.
that's all I'm stuck with, dimensional analysis.
Don't multiply.
Can you explain your reasoning again, why they're negative? Rather than what we're assuming, or rather than what we're doing?
They're negative because the field lines would be going inward,
And how do you know that?
because it's a negative charge.
They can tell you it's negative, it's not like you're
know-
saying it's negative.
Okay.
Either you get the information that's going in, or you get the information that's negative, and
And
they
then you
each
know.
other.
How about the next one?
4 plus 5.
I got
minus 10.
1/10 of what we got for S2.
112.9? Okay, now I got something for you. I'm gonna change the problem a little bit.
It's gonna screw you all over.
Oh, good.
Doesn't matter.
It doesn't matter.
Why?
Because you don't have
Not
any surface.
enclosed.
Bang,
They
bang.
change.
He added a Q4 to the description of the area.
Not
Now go.
inside any of the cooked surfaces, so it doesn't change anything.
Well, how would we know which ones are in?
Well, because
He added a Q4 at
Oh, you
the
do.
20 nanocoulombs.
It's not in the surface?
It doesn't, it's not contained within
It's
any
not
of the services
contained
he
in
gave
the
us.
surface.
So, I mean, it's in the vicinity, it's floating around out there, but it's not relevant.
Okay. Better?
That one
Is
weird
it getting
custom
more?
for you.
Yeah.
Yeah.
That's why we're home.
I'm ready to go.
Okay.
I'm ready to read liquid reviews.
All right. This is gonna be a slow process, folks. I apologize, but there's no other way that, you're gonna get.
You disagree with me?
We'll look at another example tomorrow, and then we're gonna move on